Okay, welcome back. We're moving on to chapter 12 of module C. This chapter focuses on electrolytes and different ways it can be defined, different factors that we can look for. This is all for pharmacy, by the way. So, especially when creating medication and such, it isn't always about just the weight of the drug. There's for things like electrolytes, for example, the charges can have an effect on a person's outcome, and so these need to be defined as well. And so that's why we used things like milliequivalents, milliosmoles, and we'll be going into that stuff again. Make sure you've read your part on what these things are in the slides. But we'll do a quick breakdown about that. Let's just go ahead and start with number one. Just a quick refresher of like what conversions are. That's why we're going to start with number one, okay? So one, convert a blood plasma level range of 5 to 20 micrograms per ml of tobramycin to micromoles per liter. So just before I go into it, some of you guys, we've already done some conversions where we convert to moles and such, but we need to understand that what a mole is, right? So a mole is basically just like, it's basically like the middleman conversion between the molecular weight or the grams of something to particles, basically, of a compound. So by particles, I mean atoms, molecules, a lot of other things, basically. So milliequivalence is also something that can be calculated from that middle ground, which is moles. So we need to understand how we obtain moles first before we move on to the other side of that conversion to atoms, molecules, and such. So just a background information over there. So let's just start with, this is a range. So we're going to individually have to calculate one for 5 micrograms per milliliters and one for 20 micrograms per milliliters. So let's start with, almost fell down there. 5 micrograms per ml, right? And what we want is micromoles per liter. So we're going to have to eventually convert milliliters to liters. And then what we need to convert is micrograms to micromoles. So from grams to moles, you're just using the molecular weight or molecular mass of a compound or a drug, whatever molecule. And so that's why they provide us with this molecular weight. So for every single mole, for 1 mole equals this amount, the molecular weight. And so we're going to go ahead and uh, depends the more laid out and more explanatory way to write about it is to convert this into grams first, right? So if we can do that, that's fine. Nothing wrong with that. 1 gram equals how many micrograms in a gram? It's 1 million. So I'll just write that out. Micrograms, okay? Now we can convert to moles. So for every 1 mole of tobramycin, there are 467.52 grams of tobramycin. So now we're in that middle plane. And then, so mole is the standard unit, like grams is standard unit for grams, micrograms, milligrams, whatever. Now we need to convert, so grams is crossed out, and we have moles. What we're asking for is micromoles. So we need to multiply by how many micromoles in 1 mole? It's 1 million. 1 million. How'd I get a million? There's 1,000 millimoles per 1 mole, and then another 1,000 micromoles per millimole. 1,000 times 1,000 is a million, but you can just go directly to million. K per mole. That cancels out. So now we have micromole. So we have something micromole per milliliter. What they want is micromole per liter. So, oops. To get liters in the bottom, we need to cancel it out with milliliters at the top. So how many milliliters in a liter? 1,000. Probably should have written that out. Okay. So a bunch of millions going around over there. I'll write it out, but you technically just cancel those out and then multiply the other numbers. But let's go ahead. It's totally fine. So that's 5. 5 times, where is it? 1 million times 1,000 divided by 1 million times 467.52 times nothing. Okay, 10.69. Let's just do 10.69. 10.69 micromole per liter. Okay, now we had to do the same thing for 20, right? I don't want to rewrite all that, but I know that it's going to be the same exact calculations. What I'm changing here is just the 20 here, our starting point. So for 20, it's gonna, all we have to do, calculator wise, is just go up here, enter, and then scroll all the way to the beginning. And then we highlight the 5, second, insert. So that's gonna take that, and then in front of it, insert 20. And then we can just delete the 5 right there. Okay, so that the rest of the calculation there is also included. All we had to switch out was the 20 from the 5. 4278. 4278 micromoles per liter. Now you know how to use a calculator, and now we know how to convert. So that's 1. Let's move on to number 3. Number 3 was a homework problem. Let's go over that real quick. Okay, sterile solution of potassium chloride contains 2 milliequivalents per ml. If a 20 milliliter ampule of the solution is diluted to 1 liter with sterile distilled water, what is the percentage strength of the resulting solution? So first thing I'm just going to ask is what is a milliequivalent, right? In the world of electrolytes, it's just a way of you don't define the activity of ions and its chemical activity basically by milligrams. You define it by milliequivalents, and so that's why you see things like I think it's, well, potassium actually. If you look at a bottle of potassium, it'll say 20 MEQ. That's milliequivalent rather than milligrams. So and don't ever, it's just a reminder like these things are not equivalent. So 20 MEQ does not equal 20 milligrams. It can interchange. So let's just go ahead with that. You can read more about what mill equivalents are in the slides. So we have this conversion of 2 MEQ, milliequivalents per ml, right? And then we're given 20 ml, 20 milliliter ampule of the solution diluted to 1 liter of the sterile distilled water was a percentage strength of the resulting solution. Okay, so let's start with, okay. We'll start with finding out how much total milliequivalents there are from that 20 ml ampule, right? So, um, yikes, not that much space to write with. So 20 ml times what we're given, then our conversion factor is our bridge, 2 MEQ per ml equals 40 MEQ. Okay, so we know that in this ampule, there are 40 milliequivalents of potassium chloride. Now, we need to find, that solution was diluted into 1 liter. We need to find the percentage strength of the resulting solution. So percentage strength, it's that percent that we see in topical solutions, suspensions and such. That percent is grams per liter. Those are the units for that. So, or grams per milliliter, right? Certain gram is something over 100 mLs of, let's say, water or the solvent and such. So we need to convert MEQ to grams and then have it so that it's diluted into 1,000 liters, or 1,000 milliliters, sorry. Okay, so let's go ahead and do that. Start with erasing this out, right? So we know there's total of 40 MEQ. Let me zoom this out a little bit. Maybe I can get more room that way. Yeah, I'm sure you guys can see. Go full screen. So the idea of milliequivalence charge is being considered. So let's just say for a compound like KCl, for example, right? What is like the balance or the charge of each ion? For potassium ion, there's a charge or a charge of +1. For chloride Cl, there's a charge of -1. And so what milliequivalence does is it just says that the milliequivalent of the whole compound is equal to the charge of the basically the balancing charge of the salt, the compound, right? So let's just, so if potassium is +1 and chloride is +1, then therefore potassium chloride is 1 MEQ. So let's say for something else, right? Calcium chloride. Calcium chloride, there's a charge of 2 plus on calcium, and then the opposing charge needs to balance out the 2 plus. So that's why we have 2 CLs, 2 minus. Therefore, there are 2 MEQs in calcium chloride. That's how it works. It's basically the milliequivalent depends on the charge of either cation or anion, just basically that um, opposing charges, right? Very hard to explain, I know. But we use that to determine how many MEQs are in every millimole of something, basically. So for potassium chloride, for example. All right, so to go from MEQ to um, grams, right? Because percent straight includes grams per ml or something. We need to go back. We need to look at that structure of what I said about going from grams to the middleman, moles, to particles or whatnot, MEQs. So now we're just going backwards. So we got to go MEQ. The process, it's milliequivalent. So we had to convert that to millimoles and then convert that to moles and then go to grams because it's not just equivalent, it's milliequivalent. So that being said, for every 1 millimole, remember moles or millimole is the middle ground in here. There are how many milliequivalents of KCl? 1. If you need 1 milliequivalent of potassium to oppose 1 milliequivalent of Cl, then it's the whole compound KCl is just 1 milliequivalent. It's not defined by how many particles there are. It's defined by the charge. That's all you need to worry, or valence in that example. Okay, so now we're at millimoles. We can convert that to moles. Hopefully you guys can see that. So for every 1 mole, there are, it's milli to regular, 1,000 millimoles. Okay, we're at moles. Now we can convert this into grams, right? We need to know what grams, how much the molecular weight of potassium chloride. I think it's provided for us. No, it's not. Okay, in that case, we'll just do this. Um, I'm cheating here. $74.55, let's just say that. You can look at a periodic table to determine that as well, but I cheated. 74.55 grams per mole. Okay. So we're at grams now. All we had to do is calculate. Let's go ahead and do that. 40 times 74.55 divided by 1,000. 2.982. Just write 2.98 for now. Grams. Okay. So that's 2.98 grams per 1 liter of sterile distilled water. So we got to divide that. Okay. 92 divided by 1,000. So that equals 0.00298 grams per ml. Up to you how you want to go about it. You could just multiply it by 100 and just say that's percent. So let's just show it to you like this. For I were to multiply 100 on both sides, you get 0.298 for every 100 ml. I see that and I immediately know that this is going to be the same thing as the percent. 0.298%. Or you could just add that and then multiply by 100, and then you know that's also the percent. Just how you see it. You know, it could be different. But yeah, that's the answer. You could have gone it like this, or you could have gone by. I think proportions could have worked for that as well. I like to see it better this way. It's just up to you. Again, preference. Okay. Next question. Question 5. How many milliliters of a solution containing 2 milliequivalents of potassium chloride per milliliter should be used to obtain 2.98 grams of potassium chloride? So we're given a amount of potassium chloride, 2.98 grams. They're asking for milliliters of a solution containing a certain strength per ml. So that's based on like how we've been approaching these problems, we know that 2 MEQ per ml is our conversion factor. We just need to understand when are we going to implement that conversion factor, right? So we need to think, okay, it says 2 MEQ per ml. We need ml, so we're probably going to be using that towards the end. So how do we start with getting MEQ with grams? So that's how you should be approaching this. Okay, so we start with 2.98. Where should I write this? Write this a little bit on the top, actually. Let's do that. Like this. So for number 5, right? That's 2.98 grams. So how are we going from grams to milliequivalents? We had to use our middleman, which is moles. For every mole, there is, how much did we say? 74.55 grams of KCl. So now we're at moles. For milliequivalents, we need millimoles, right? Yes. And then always make sure you take a step back and find out how much milliequivalents they are, because they might give you a different compound and with a different valence or charge, and then that could be a different milliequivalent factor, right? So KCl, it's one charge that's for either cation or the anion, so it's one milliequivalent, right? So there is 1 milliequivalent per millimole. Okay, so now we're at milliequivalent. We can just like stop right there, get our answer, and then we use 2 MEQ per milliliter to get milliliters, right? but we can just also do that in one step. I just wanted to show you how we're approaching this, right? Why we're continuing. Jeez, I think I'm dyslexic after 10 p.m. Why we're continuing from here. So 2 MEQ per ml. So for every 1 ml, there is 2 MEQ. That's the to say just like the quantity per volume that they desire based off of what we had. So everything cancels out, grams, moles, millimoles, and milliequivalents. They're only asking for ml. So all we had to do is put it in our calc. 2.98 times 1,000 times, just kidding, divided by 74.55 times 2, 74.55 times 2. Okay, what is that? 19.98. Can do 19.99 ml. We can do 20 ml. Close enough, right? Sig figs aren't specified. It could be either or, honestly. Just really depends on who's grading, right? So yeah, that's this just is showing you how we're going from the beginning, how we're starting from the beginning, or if we're starting from the end, right? Whether we're starting with grams or whether we're starting with milliequivalents. How do you, what's the path? How do you go by it, right? Your first step is just to say, how am I supposed to reach moles? And then you can say, oh, okay, from there, I'll be able to calculate grams, or from moles, I'll be able to calculate milliequivalents. So, plan of attack. Next, number 8. Number 8 is not a homework problem, but I also wanted to have that for a specific reason here. How many grams of potassium citrates? They give you that formula and it looks confusing, right? But just from the name of the compound, potassium citrate, we can deduce or infer that potassium is one part of the charge and citrate is the other. And then we're looking at the compound. There are 3 potassiums. So that probably means that citrate has um, a 3 minus charge for it to balance out with 3 potassium. So milliequivalent wise, it would mean that there are 3 milliequivalents. That's just thinking ahead, right? But that's how we're looking beyond the numbers themselves. We need to read that. Comprehension is a big factor into getting the right answer. So back to the problem. How many grams of potassium citrate should be used in preparing 500 ml of a potassium ion elixir so as to supply 15 MEQ of potassium in each 5 ml dose? So we are given a volume, total quantity. We have a conversion factor, and we're looking for grams. So how do you approach this, right? Can we go from ml to grams? Probably not this way. We can use MEQ to go to grams, right? Go from MEQ to moles to grams. So let's go ahead and do it that way, right? So first we need to find out how many, the total amount of MEQ in this solution, right? Or elixir. 500 ml. And then 15 MEQ. per 5 ml. Okay, so once we multiply that out, that will give us our total amount of MEQ, but we can continue on from there because we know where that goes. So from MEQ, we want to get millimoles. So like I said, uh, this is a compound that isn't charged. It's balanced out. So we know that if there are 3 potassiums and potassium each has a +1 charge, citrate probably has a 3 minus charge. So 3 plus 3 minus, right? So there probably is 3 milliequivalents in this compound. So just because we're going backwards, for every 1 millimole, there are 3 milliequivalents of potassium citrate. And then we just go ahead and get to our standard moles. So for every mole, there are 1,000 millimoles. And then for moles, we can go to grams. They give us our molecular weight, 324 grams per mole. Cool. So plug and chug, 500 times 15 times 324 divided by, put that in parentheses, 5 times 3 times 1,000. It's taking me time because it's at a weird angle from the computer here. 162. 162 grams of potassium citrate. I'm not writing all of that out. Yeah, that's correct. Any questions? How would I know, right? um, See that? I mean, that was just an example of us going backwards. Our last question, we started with grams. Now we were technically just starting with milliequivalents, going back. So yeah, just like have that mental in your head, like when dealing with electrolytes and solving for milliequivalents and such, or dealing with milliequivalents, check for how many milliequivalents there are, and how do I get from this to moles to whatever. 2 things to consider. All right. Next one, 14. Skip a couple problems here. Ooh. So much highlight. All right, 14. Ammonium chloride is to be used as a urinary acidifier with a dose of 150 MEQ. How many 500 milligram tablets should be administered? So we're just given a MEQ, right, for ammonium chloride, and we need to divide that as tablets, right? So we need to get from MEQ to grams, right? And then based off of grams, we can divide them into tablets to just find out how many tablets there are. Very simple. We've dealt with problems like this before. So given 150 MEQ. It's another example of a problem going backward. Times for every millimole. Ammonium chloride. What's the MEQ? pretending this is like another episode of Dora. Yes, one MEQ. Okay, so MEQ millimole to mole. We've been doing this a few times. For every mole, 1,000 millimoles. And then from moles to grams. How many grams in a mole in this mole? 53.5 grams per mole. All right, so let's find out what that is. $150 times 53.5 divided by 1,000. 8.025. Grams. Okay. And so that's the total amount of ammonium chloride in terms of grams. We need to divide these into tablets, each one being 500 milligrams. So this is in grams, first of all. Multiply this by 1,000. This equals 8,025 milligrams divided by 500 milligrams per tab. So when you're dividing a fraction like this, you're basically multiplying by the reciprocal. So tab is on the top now, and then the milligrams cancels out, right? Cool. And so you're left with tabs as a unit. All we had to do is calculate this now. 25 divided by 500 equals 1605. So 1605 can't give 1/20th of a tablet. So let's just say about 16 tabs. So it takes 16 of 500 milligram tablets, 16 500 milligram tablets to equate 150 MEQ of ammonium chloride. That's the whole shebang. All right. Next one. 17. Okay, so 17. 17 is what my slides look like when the professor says to highlight the important stuff. That's quite a bit there. All right, well, let's get right into it. Take a seat. At 3 o'clock p.m., the pharmacist received an order to add 30 MEQ per liter of potassium chloride to the already running intravenous fluid for a patient. After checking the medication order, the pharmacist found that the patient is receiving a 5% dextrose to 0.9% sodium chloride infusion at a rate of 85 milliliters per hour, and that the patient's liter of fluid was started at 1:30 p.m. Okay, so what does that tell us? That's just basically saying that from 1:30 p.m. to 3 o'clock p.m., there's already been a certain amount of 5% dextrose to 0.9% sodium chloride, which, by the way, is the same thing as D5NS, right? Dextrose 5%, And then NS is normal saline, which is 0.9% sodium chloride. So there's a certain amount of that already being infused into the patient. That means there's a little bit less than a liter um, left in that IV. So that means that to achieve 30 MEQ liters of potassium chloride, we would probably need um, a lesser amount of MEQs to be administered. So, because originally we had a liter of fluid, right? So we could have just said, oh, let's just give them 30 MEQs. But now there's a less than a liter left. So based off our concentration of achieving 30 MEQs per liter, we need to give something less than 30 MEQs to achieve somewhat that same concentration. Capiche? Sounds like a lot, but let's just go ahead with the uh, number wise and then see what if it makes sense, right? So with A, assuming that it took 30 minutes to provide the needed potassium chloride to the floor nurse, how many milliequivalents of potassium chloride should have been added to the patient's running IV fluid to achieve the ordered concentration? So that follows that idea of, okay, so now there's 30 minutes being added, right? So from 1:30 to 3 p.m., that's an hour 30, and then 30 minutes is enough. So that's 2 hours total. So we need to find out um, how much was all, how many mLs from the liter of solution was deducted and infused in the patient. And then we need to find out how much is left over in that liter. And then from that remaining amount, we need to find out the concentration, the MEQ of potassium chloride that needs to be infused because now there's um, less of the IV, so we need to give less MEQ to match this concentration, 30 MEQ per liter. Okay, so let's first find out how much has been deducted, right? All right. So we said that it took about 2 hours based off the 1:30, 1.5 hours from here, and then extra 30 minutes to deliver it to the nurse. So it took about 2 hours to, um, it took 2 hours for the patients of infusing from the original IV solution. So let's find out how many mLs that is. So 2 hours times 85 mLs per hour. That is 160, 170 ml. So that's how much IV has already been used up. We need to find out what's left over. Okay, so we started with the patient's liter of fluid. So we started with a liter. That's 1,000 ml minus 170 ml. That is 830 ml. Okay, so we want to maintain this rate, concentration, whatever you want to call it. So, but we also want to find out how many MEQs it now is from this remaining quantity. So we just multiplied it out. But we just need to know that this is 830 milliliters and the concentration is in liters. So 830 divided by 1,000 is 0.83 liters times 30 MEQ per liter. That equals, let's do the math, 0.83 times 30, 24.9. MEQ. So what does that mean? That is now the adjusted MEQ that needs to be administered into this IV of 830 milliliters now to maintain that same concentration of 30 MEQs per liter. Okay? Hopefully that makes more sense. All right, so that's A. B is asking how many milliliters of an injection containing 2 milliequivalents of potassium chloride per ml should have been used to supply the amount of potassium chloride needed. So we have um, quantity of milliequivalents, but that isn't a viable like quantity that we can administer with, right? We need to use milliliters or weigh it out in grams and such. That's why we use the 2 MEQ potassium chloride per ml, so we can find out how many milliliters that is. So for B, write it over here, we have 24.9 MEQ times, let's see, for every ml, there is 2 MEQ. So answer for that's 12.45. 12.45 mLs of potassium chloride. So that's B. Okay. So let's get into C. C is kind of the reason why I wanted to go over with this monster of a problem, because it goes into osmolality. And so osmolality and osmolarity actually are two ways of defining osmotic pressure. So they use something called osmoles. It's that's really what's defining the osmotic pressure, and it's very similar to milliequivalents in terms of conversion wise, but there's only one difference. So milliequivalents, like we said before, is determined by charge. So the charge of KCl, for example, there's plus 1K, minus 1C. So the charge is the relative charge is just 1. And so that is why the milliequivalent is 1. Osmoles and milliosmoles consider all particles in that compound. So for KCl, there is 1 part KCl, sorry, 1 part K, 1 part Cl. So there are 2 parts into that compound. Therefore, 2 osmoles, 2 milliosmoles. Um, so that's the idea when converting. So for every millimole of KCl, there are 2 milliosmoles and such, depending on the compound and such. For that's for compounds that can dissociate, right? For compounds that don't dissociate, like dextrose, for example, it just remains as 1. That's the ongoing idea that we've had so far with a lot of these calculations. Um, why milliosmoles, right? So we said that these are defining osmotic pressure. Osmotic pressure is the ability of water to diffuse from a solvent with low concentration to a solvent with higher concentration. Why would you want to go from low to high, right? Because usually we've always heard, when we hear diffusion, we hear high to low, right? But water is the solvent. We're not considering the solute now. Water is the solvent. So water is the factor that's being used to reach equilibrium. It would want to go to somewhere with higher concentration to balance it out. So it's relevant for things like electrolytes and things that associate, and that's why we need to understand how it works and how to calculate it. So with osmolality, we're just basically considering all osmoles in a equation, and yeah, all osmoles, milliosmoles in an IV, and then adding them together. So let's go ahead and just understand what we're calculating, right? So what was in the the IV? There was potassium chloride, there was dextrose, and there is sodium chloride. So we need to find the milliosmoles of each factor and then add them together. So let's start with um, let's start with sodium chloride first. Okay, so sodium chloride is given to us as a percentage. So let's write this here. 0.9%. So that's equates to what? 0.9 grams over 100 ml. And then in a liter solution, we can multiply that out. So times 1,000 ml. And that way we get grams. So we multiply this out. That's 9 grams of, what is it, sodium chloride equals 9 grams. 9 grams. And then from 9 grams, we can calculate milliosmoles. It's a very similar conversion to from milliequivalents. So 9 grams times sodium chloride. Don't remember. What was it? Of NaCl. 58.44. Oh, probably need to go back. So for every mole is 58.44 grams. And then millimoles. So there are 1,000 millimoles per every mole. And now we're at milliosmoles, right? So NaCl, 1 part Na, 1 part Cl. So there are 2 parts being considered for milliosmoles. So 2 milliosmoles. M capital O S M O L, milliosmole per millimole. Okay, let's calculate that. 9 times 1,000 times 2 divided by 58.44. So 300, let's just say 308 milliosmoles. Okay. And then, so that's for NaCl, sodium chloride, or more saline, whatever you want to call it. Now we need to do dextrose. All right. So same idea. I'll start here. So 5% dextrose, that's, I'll just write it all out, that's fine. So 5% dextrose, that's 5 grams over 100 ml times a liter, 1,000 ml. So that equals 50 grams of dextrose. Okay, 50 grams of dextrose times 50 grams of D times 1 mole. I probably need to find out the molecular weight of dextrose. So let's do that. I think I've actually might provide it for us here. Oh, it is. There you go. We had the other one there too. So 180.2. Let's adjust this. Where are you? $180.2 grams times 1,000 millimoles per mole. Writing over the questions. Hopefully you can read that. Times, okay, dextrose. Dextrose isn't a compound that even dissociates. So it wouldn't dissociate into two different particles or two, three, whatever particles. It just remains as one particle. So that's just 1 milliosmol to worry about. So there are 1 milliosmol in 1 millimole. Go ahead and calculate that. 50 times 1,000 divided by, can't read that, 180.2. 277. 277.47 milliosmol of D. Okay, now we need to find the milliequivalent of potassium chloride. So, or milliosmol, sorry. What do we use, right? Um, we have a uh, conversion, what the 30 MEQ per liter, and so we could just use that and converted that into milliosmoles per liter as such, right? So let's go ahead and do that. $30 MEQ per liter times it was adjusted for less than a liter, but it is considered for a liter. So we would also multiply it out by a liter. 1 liter. That cancels that out. Now we want to get milliosmoles, right? So we need to turn this back to millimoles and then go to milliosmoles. So for potassium chloride, there was, for every millimole, there was 1 milliequivalent. But in terms of milliosmoles, there are 2 milliosmoles for every millimole. Okay. So that being said, 30 times 2. 60. Didn't even need a calculator for that. 60 milliosmoles of KCl. So we have all these milliosmoles. All we just have to do is add them all up. So let's see. There is 308 milliosmoles plus 277. Let's say, or we can use the actual amounts, right? This plus this plus 60. 645. Yeah. So write that out here. 308 plus, let's just say 277, yada, 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 plus 60 equals 645. Yes, just about. So that's the amount of osmoles. Something with molality is per kilogram usually, right? Um, we have a liter of solution. So grams per milliliter. There's 1,000 milliliters, so there's 1,000 grams, which is equal to 1 kilogram. So 645 osmoles per 1 kilogram. That's the osmolality of this solution. It's quite a bit, but just something to consider. All right. Very messy. Hopefully you guys can organize it quite a bit better than I did. Okay, so moving on to 22. Calculate the daily water requirement for a healthy adult weighing 165 pounds who is 5'10" tall. It's there, it's highlighted. It's probably going to be in the exam. I would go over it, right? I don't drink enough water per day, so it's probably important for me to do this anyways. So let's go over it real quick. We aren't given an equation for that in the equation sheet, but we are told that there is generally 1,500 ml of water per square meter of BSA. So we can multiply that unit by our own BSA, and they're giving us pounds and height. So we kind of need to, based off of our previous experience with that, we can probably assume that BSA is involved. We can multiply that 1,500 mLs per meter squared by our own BSA to determine the amount of water that we should be consuming per day. Because it should be specific per person, right? Based off of different factors, someone's weight, someone's height, and such. So let's write out that equation first. Water requirement equals 1,500 ml per meter squared times BSA. Okay, so step one, we need to find BSA. What is the equation for BSA? BSA equals, whoops, kilograms, weight of a person, times his or her height, centimeters, over 3,600. So a couple conversions that we had to do first. 165 pounds divided by 2.2. That'll get us kilograms. And then 5'10". 5 feet, 12 inches per foot, that's 60 inches, plus another 10 inches, that's 70 inches. 70 inches times 2.54 centimeters per inch. We'll find that out too. So let's get right into it. 165 divided by 2.2, 75 kilograms. 70 times 2.54, 177.8 centimeters. 75 kilograms, 177.8 centimeters. So plug and chug. Let's put that here. Equals 75 times 177.8 all over 3,600. So we can use our calculator in one go. This, put this in parentheses. 75 times 177.8 divided by 3,600. So 1 point, let's, writing sake, let's put 1.92 meters squared. We're not done. That's BSA. We want water requirement in milliliters. So we just multiply our BSA by 1,500 times 1,500. So just to finalize here, water requirement equals 1,500 ml per meter squared times 1.92. That equals about 2,886 ml. If you want to be specific or more relative, about 2.9 liters. And, you know, run accordingly and whatnot, depending on what you need it around to. So yeah, that is chapter, I think that was 12. Yeah, chapter 12, end of module C. We'll be going ahead with module D and last module of the series. We've come a long way. I'll see you at the next one.